Hi, my name is Kimi Okuno. I'm assistant professor at the Institute of Statistical Mathematics and visiting researcher of Riken Center for Advanced Intelligence project. Today, I'm going to talk about a greedy and optimistic approach to clustering with a specified uncertainty of covariates. And this is a joint work with Dr. Hattori, a researcher of astronomy. And so far, we published these two archive manuscripts. Today's talk mainly focuses on the methodological aspects of the proposed method called greedy and optimistic clustering. So please see the first manuscript for the methodological aspect. And actually, the proposed method has been applied to the statistical clustering analysis in the field of astronomy. So if you're interested in the application, please refer to the second manuscript. Okay, anyway, let's get started. And at first, I'd like to describe the background of this study. Actually, this study has been started from a small talk with Dr. Hattori, who is unknown to the Institute of Statistical Mathematics. He's a researcher in the National Astronomical Observatory of Japan, so the problem setting of this study is mainly based on the real data used in the field of astronomy. So, okay, I'd like to describe the detailed problem setting. In this study, we consider clustering of stars. And, many stars distribute in our universe, and we can obtain the position and velocity of these stars by using observatories. So, as an example of the dataset we consider in this study, we assume that we have observed three-dimensional position vector and the three-dimensional velocity vector for each star. Namely, we have six-dimensional observation for each individual star. But as you know, the observed quantities may include some uncertainty. For example, if we observe the position of stars, there exist some observational errors. It is particularly important to consider these uncertainties in the field of science, as these uncertainties can easily change the scientific conclusion of research. And the observation of stars have an interesting property. As you know, there are many stars in the universe, so some stars may be distant from our solar system, and some stars may be close to our solar system. And as you can easily imagine that the distant stars may include larger uncertainty than the closer stars belonging to our solar system. So the observational uncertainty is also individual to each star. Distant stars may have larger uncertainty, and closer stars may have smaller uncertainty. So in this talk, the individual star is represented by an index I, and each star is assumed to have some probability density pi. And we specify some threshold epsilon here. And then we define the uncertainty set Zi for each observation. So this is the first setting. And we assume that we have observed the uncertainty set Zi for each star I. And typically we assume the normal distribution for the probability density pi. Okay. And then we describe the second setting. In the analysis of astronomy, nonlinear preprocessing is particularly important. I mean, we transform the raw observation to some feature vectors by using some physical transformation. Please look at this example. The left one shows the stars of the developing galaxies. Dr. Hattori conducted a numerical simulation of the development of galaxies. And as you can see, stars in each galaxy A and B are gathered at the same time, gathered at the time zero here. But so namely, the position and velocity of stars in the same galaxies are the same. But as time progresses, the position and velocity of stars are also changed by their interactions. I mean, position and velocities of stars are developed by their interaction. So the position and velocity of stars are mixed as time progresses. However, it is known that a quantity called orbital action that can be computed from the position and velocity is conserved with the elapse of time. As you can see in the right-hand side, the orbital action of each star seems to have a good cluster structure. So in this study, we consider applying a nonlinear transformation to the observed quantities so that we find a good cluster structure of stars. And actually, the transformation here, of observation to the orbital action, can be computed by using some published softwares. Dr. Hattori also computed these transformations. Okay, so let's wrap up these two settings. As we described at first, we observe a covariate ZI that represents the observation-like position and velocity of stars. The observation may include some uncertainty, and typically we assume the normal distribution for this uncertainty. And we define an uncertainty set large ZI. The realization of the covariate is expected to take a value in this uncertainty set. And if we assume the normal distribution for a probability density pi, then the uncertainty set should be formed like this ellipsoid. And as also we described, we apply a nonlinear transformation to the observation to obtain a conserved quantity. Here we apply a function f. We use the symbol xy, this one, to represent these transformed features. Then we may obtain an uncertainty set for the transformed features. The uncertainty set for transformed feature is no longer ellipsoid. This set is even non-convex, and it is quite difficult to utilize such a non-convex uncertainty set. Okay, and here, as an example, I show a two-dimensional PCA plot of the conserved feature and the uncertainty set. Each gray curve represents the discrete feature uncertainty set for each star. And obviously, as you can see, the uncertainty set for features is non-convex. We would like to apply clustering algorithms to these features and uncertainty sets. Okay. And from application perspective, this study develops the existing studies of Dr. Rodler. In the paper of Rodler 2018, he collected the observations of 83 stars, and among these 83 stars, he first removed 48 stars having large uncertainty. I mean, he used only 35 stars having small uncertainty. But in our subsequent study, we apply clustering to all the 161 stars, including all the newly observed stars, and stars having even larger uncertainty. And actually, our result is consistent with the previous Rodler's paper. And we find many new clusters. We skip the detail of the application perspective, but if you are interested in this application, please look at our subsequent paper written with Dr. Hattori and Dr. Rodler. This page shows summary of previous study of clustering algorithm using uncertainty set from methodological perspective. In my view, there are roughly two different types of existing studies. The first type is considering the average of covariate uncertainty. I listed several existing studies. And maybe the closest study to this talk is UK means. Maybe UK means stands for uncertainty K-means. And K-means is a kind of classical clustering algorithm. And if there are probability densities of the features, UK means averages the loss function of K-means algorithm over all the probability densities of features. Maybe this is a natural solution of using the uncertainty set, but actually these methods assume that the probability densities are normally distributed. So they are not compatible with the probability setting, because probability density of features in this study is no longer normal distribution because of the nonlinear preprocessing applied to the observations. And the second one is considering the worst case of the risk of clustering algorithm with respect to the covariate uncertainty. This type of algorithm is also known as robust optimization, and it is also developed in the field of mathematical optimization for these 30 years. Bo et al. 2016 applied this robust optimization technique to clustering problem. We call this robust optimization as pessimistic clustering, as it is based on the pessimistic attitude of optimizing the loss function of the clustering algorithm. Okay. However, these existing studies are not comparable with our problem setting. As you can see, the uncertainty set in our problem is like this. So there is, roughly speaking, no meaning to take average over the uncertainty set. And actually, some scores are not that good when using the first type of existing algorithms, including UK means. And also the pessimistic one, the latter one, that incorporates the robust optimization to clustering results in devastating output. Roughly speaking, for most cases in our problem setting, the pessimistic clustering algorithm outputs only one big cluster. Of course, concluding the number of clusters is one can be regarded as a kind of conservative conclusion. But in practice, there's no meaning. We want to find some clusters. We don't want such a big one cluster as a result of clustering algorithm. So we propose a clustering algorithm to deal with the uncertainty set properly. And our idea is very simple. Our idea is optimizing the best case of the clustering loss. Namely, we employ an optimistic perspective for a clustering. We propose a greedy and optimistic clustering algorithm, and we call it a GOC algorithm, shorthand. And please look at the left figure. In this figure, each gray area represents the uncertainty set of each star. And in our analysis, we first take some feature representatives in each uncertainty set. As you can see, there are 5 stars with uncertainty set in this example. So we pick one feature representative for each individual star. Then there are 5 feature representatives here. So we can apply some clustering algorithms to obtain the temporal cluster. Then, as you can see, we have obtained 2 clusters in this step here. Then please look at the second figure. In this step, we contemplating the cluster feature candidates. In this step, we compute the distance between the uncertainty set and the cluster centers. Distances between the members of uncertainty sets and the cluster centers. Then we update the feature representative in each uncertainty set so that the minimum distance from the members of uncertainty sets to the center of clusters is minimized. Here, the feature representative of star 3 is reassigned to near the cluster 1. Then we again apply the clustering algorithm and we obtain new clusters. Then we repeat these steps. Please look at the last figure. Using this iterative algorithm, we expect to obtain such a kind of clustering having smaller radius compared to the initially obtained clusters. As you can see, the radius of the clusters in the final step is much smaller than the previous ones. So this is Yoshi algorithm. And as you can see, we may employ arbitrary clustering algorithm for the clustering step here. For instance, K-means, GMM, Gaussian mixture modeling, mean shift, or something like that. So our proposal is compatible with many existing algorithms. Okay, this slide shows more rigorous procedure. In our first step, we make a discrete set approximating the uncertainty set. This one is simply obtained by generating some instances of covariates and applying the nonlinear transformation F to the covariates to obtain features. Okay, and then in the second step, we repeat these three steps. We first initialize the feature representatives. Then we apply clustering algorithm to the current representatives. Then we compute clustering centers and assign new feature representative to minimize the minimum distance from the uncertainty set to the cluster centers. So this is the GOC algorithm. And actually, introducing the optimistic perspective to statistical method is not that new. Similar approach can be found. Maybe the most famous one is called Deming regression, solving so-called errors in variable regression. As you know, most of standard regression problem considers a covariate without error, but in errors in variable regression, errors are included even the covariate. Covariate is represented by X here. Then the classical Deming regression, proposed roughly 150 years ago, considers maximizing the log likelihood and then define the Deming regression estimator like this. As you can see, the Deming regression estimators considers a regression to predict Y from the selected representative tilde X that are selected near the observation X. So our method also can be regarded as a clustering version of this kind of Deming regression. Okay, from here I'd like to describe the experiments. In our experiments, we used a realistic dataset computed by a numerical simulation. And actually, this dataset is publicized in my GitHub repository. So if you're interested in this dataset, please refer to my GitHub account. And this dataset consists of 10 instances. In each instance, there are 275 stars, and they have three-dimensional orbital action features that are already pre-processed nonlinear. And each star I has an uncertainty set that is represented by 101 discrete points. And these stars are generated by numerical simulation. So if stars have the same birthplace, they have the same class level. I mean, the class levels can be used to evaluate the clustering results. And as for the baselines, we employ clustering with feature representatives that are computed by averaging the uncertainty set. So the baseline can be regarded as a slight modification of the existing study called UK-means algorithm. Okay, this slide shows the experimental results of clustering. The underlying number of classes are 50, and we specify the initial number of clusters as 50 as well. Then we evaluate the proposed GOC and the baselines by the normalized mutual information and F measure. Higher scores are better. Then, as you can see, the clustering scores of the proposed methods are better than baselines. And here, lambda denotes a weight for penalty function for the feature representatives. We use the penalty function for the feature representatives so that near the center of the uncertainty set have small penalty, and the distant features from the center of the uncertainty set have large penalty. So if lambda is large, for instance, lambda is equals 1, then feature representatives tend to be selected from the center of the uncertainty set. Then the results also indicate that the smaller penalty is better than the larger penalty. Okay. And consequently, in this experiment, the proposed optimistic clustering equipped with k-means clustering is better than the conventional k-means, UK-means, and the pessimistic version of the k-means algorithm. Okay, we also conducted clustering analysis with different number of feature clusters. As I described in the previous slide, the underlying true number of clusters is 50. And by setting the initial number of clusters by k0, then the results of GOC algorithms are shown here. In any case, the proposed GOC algorithm improves the clustering scores compared with the baseline. Okay. This slide shows the convergence of the proposed GOC algorithm. And please look at the left figure, this one. And this left figure shows the convergence of the temporal cluster assignment to the final cluster assignment. And actually, roughly 15 iterations is needed for exact convergence. But as you can see, if 2 or 3 iterations are done, then the cluster assignments are almost converged already. So I here emphasize that only 2 or 3 iterations is needed to improve the clustering results. So the computational cost is not much larger than the existing studies. Actually, only the twice or triple of the computational cost of the existing clustering method is needed to compute GOC algorithm. And actually, I also think that the computational complexity of the GOC algorithm can be further reduced by good implementation. Okay. And here, this slide shows the clustering results of GOC algorithm using different clustering oracles, including K-medois, that is a similar approach to the K-means, and GMM, Gaussian mixture modeling, with implementations called cluster R and M-class, something like that. Okay. And in any case, as you can see, the clustering results of the proposed GOC is improved from the baselines. Okay. So far, we confirmed the proposed GOC algorithm by using the synthetic dataset. So at last, I'd like to show a small part of real-world dataset analysis briefly. Okay. This slide shows the clusters found by GOC algorithm applied to real-world datasets. We applied the proposed GOC algorithm to the dataset of 161 real-world stars observed in the observatories. And as I explained, this dataset is an extension of the dataset used in the previous study written by Dr. Rodler. And please look at the right-hand side here. As you can see, there are some capital alphabets here. This alphabet indicates that, for instance, in the second line, the cluster 2 found in the GOC algorithm includes the stars found in the previous study, Rodler 2018. For instance, the cluster D found in Rodler consists of 3 stars, and 3 out of these 3 stars belong to the cluster 2 in the GOC output. As well, many clusters found in Rodler are covered by our clustering results. And also, our GOC algorithm additionally found many new clusters where the members are not observed in the previous study. So this is the result of our real data analysis. So if you are interested in this real data analysis, please refer to our new archive paper. Okay. So this is our conclusion. In this talk, we proposed a GOC algorithm that considers uncertainties for each individual. And the proposed GOC is applied to a synthetic realistic dataset. And we evaluate the GOC algorithm using this dataset, and the clustering scores are also improved. GOC is also applied to real-world dataset already. And the result of the application to the real-world dataset is shown in our subsequent study collaborated with Dr. Hattori and Dr. Rodler. Okay. Anyway, thank you very much for listening.